session, and this will be, as I was mentioning before, this will be Kubernetes Deconstructed, the AWS edition, and it's going to be delivered by Ninant Pundalik. Ninant is actually an engineering manager at Slack, the program that you use for chatting internally in the office or other groups. He has more than a decade of IT experience. And when we asked him how he would like to describe himself, he said that he likes to learn systems by tearing them down and building them back up. And because of this, his toys never lasted more than a year. So I guess I understand where his love for deconstructing Kubernetes comes from. So let's have a quick look and see what Kubernetes Deconstructed, the AWS edition, is by Ninant Pundalik.
Hey, hi, my name is Ninat Pundalik and welcome to the next session in the AWS Community Day South Asia Virtual Edition 2021. I hope you really enjoyed learning about SageMaker and DynamoDB in the session that just happened and are really excited to learn a little more about Kubernetes in this session that we're going to be spending another 30 minutes on. Before we begin, like with anything that happens in India, I'd like to take a couple of minutes for a small prayer. I very rarely listen to Western classical music, but when I do, I try to find out music that was composed by Beethoven. Beethoven is a composer who lived about 200 years ago and is considered as one of the masters. He reached mastery because he did not just practice music. He forced his way into its secrets and then got to a level where the compositions he wrote at that point of time are considered one of the best even today. In the same way, as an engineer, I like to understand what's happening at least one or two layers beneath the systems that I'm working on. And only when I can force my way to those layers and understand how those components work, can I be an effective and competent engineer. I hope that at the end of this session, you build a better mental model of how Kubernetes works and feel more confident in tackling a lot of the complex demands our product roadmaps place on us. And you don't just poke around at random things to figure out why something is not working, but understand why stuff is not working by systems thinking and first principles. In today's session, we're going to be looking at Kubernetes from a few different perspectives or from the eyes of a few different people. First off, we look at Kubernetes as a user. We've been doing that for all this while, so you know how to interact with Kubernetes. Next up, we'll spend some time looking at how a cluster operator thinks about Kubernetes and what do they need to do to make sure Kubernetes is healthy and performant. After that, we'll take a look at how a network provider looks at how their various components hook into Kubernetes and how they can ensure that anything that's running on Kubernetes is successful. Lastly, all of us or most of us present here today are going to be working with cloud providers like AWS. We'll take a small journey through what are the different options available as consumers of cloud providers, as well as take a brief moment to understand what a cloud provider itself would need to make sure Kubernetes works successfully. Let's start our journey with how a user thinks of Kubernetes and how they end up interacting with a cluster. Before we get into how a Kubernetes user interfaces with a cluster, we want to briefly walk through containers because it sets the stage for everything we're going to look at going forward. A container is usually a bunch of different files and folders that are packaged together. The package then contains a bunch of metadata that is associated with it. Usually you have environment variables that are going to be needed for the application, the command that you're going to run to actually execute the application you're interested in, what ports to expose to the world outside the container, as well as any volumes or disk mounts that need to be attached to the container for it to do its functions. It also has a bunch of different labels associated with it, and this is our simple application server. You can have an application server. You can also have a metrics server as running as your container. You could also have a service mesh container, which is used to route traffic across various systems. And a container can also have different volumes that are associated with it. The container itself is usually not very helpful for us because we want to know how our health services, is it healthy, and so on and so forth. And this is where Kubernetes adds an additional construct or an additional layer of abstraction, which is known as a pod. The pod, as you can see over here, has 3 containers in there, and it also supposed to have a disk, but I don't know why it doesn't show up over here. You can also have a very simple pod. It just has one container in it. It could be your application container and your metrics container. It could be a simple container that processes a bunch of different data. But this is a much more realistic example of a pod with a bunch of different containers and storage volumes. Going forward, we're no longer going to look at what is an individual container, and we're going to think of just pods. And a single pod is rarely ever useful for web scale traffic. You would want multiple pods. And Kubernetes provides us an abstraction object on top of pods, which is known as a deployment. A deployment comes with a few different metadata. There's the image, which is the most important for us. It tells us what is the actual application or the container that we want to run inside this deployment. And it also contains a bunch of different selectors. When you give Kubernetes this data, it'll end up spinning a bunch of different pods, and then it'll also spin up a service if we've asked it to. As you can see, the service has a selector, and that selector is used to route traffic to the pods in our deployment. Similarly, when you have when you decide, hey, I want to update the image that is running in all of our containers, I want to deploy a new version of my application. You go ahead and tell Kubernetes, hey, can you update the metadata of the deployment? At which point of time it will go ahead and kill one of the pods in the deployment. It will stop routing traffic to it, so the service knows how to take care of that. And then it will spin up a new pod, which the new version with the newer image, and then the service starts routing traffic to the new pod. The same happens for the other pod, and then eventually all of the traffic goes to the new version of the application we've just pushed out. And when you want to route traffic from the internet to the service, you use an ingress object. An ingress object will route traffic to a service, and from the service, the traffic is further routed to the pods, as we just saw. A user ends up using a URL and either a username, password, or a bearer token or a client certificate to talk to the cluster. And when they talk to the cluster as a simple user, I'm just going to use kubectl, and I'm going to go ahead and create a namespace on the command line. And I'm also going to give it a bunch of YAML files to create different resources. A few example resources that we're going to use right now are, here's a deployment of the object that we just saw. Here's another that's a service object that we need. And finally, an ingress object. We take all of this and we pass it on to Kubernetes. And Kubernetes has gone ahead and created the various resources we've asked it to. There's the ingress, the service, and the deployment. But you will also notice that there are a bunch of other things that have spun up, which are the pods that are absolutely necessary for the actual requests that we've asked Kubernetes to be satisfied. And with this, the end of the journey for a basic user of Kubernetes. Next up, let's figure out how a Kubernetes cluster administrator needs to work and needs to worry about. There are a bunch of different things around this that are really important, but most of all, Kubernetes is highly configurable. There are a bunch of different ways by which we can configure Kubernetes. You can configure it by providing it a lot of different options. You can add plugins to it to change the behavior for certain aspects of it. You could also completely replace some parts of Kubernetes and make it behave the way you need them. Throughout the next few slides, I'm going to be using these icons, so just keep an eye out for them whenever they show up. We just sent Kubernetes a bunch of different resource definitions, and it ended up creating a lot of different resources. But what actually happens when we go ahead and send these requests? And what is Kubernetes? Let's begin. Kubernetes, the object service that we think of, is usually comprised of these different components. There's the API server, which is the front gate for everything that we end up working with. There's the scheduler, which is sort of like the brain of what's happening in Kubernetes. There's the controller manager, which acts as the coordinator. It makes sure that everything is running the way we need them to. The kubelet is most likely a good example of what happens as a heart. And then there's the proxy. And all of these can be configured in various different ways. Let's take a look at what is the API server first. Whenever we go ahead and create kubectl requests or kubectl commands, they end up connecting to the API server. The API server will take in a bunch of different definitions, and it will spit out a bunch of different resources. It can also take custom resource definitions where you can go ahead and create your own format for a resource, and then Kubernetes will accept those and it will work with them. The API server ends up talking to etcd to store all of the requests that it has received, as well as the health and the state of all of those resources. Most of the times, it's not a single etcd, it is a cluster of etcds to ensure that there's high availability as well as disaster recovery that's supported in the Kubernetes cluster. So that's the API server. The scheduler is where things start getting really interesting. The scheduler keeps a watch on all the events that are happening in the API server and then goes ahead and figures out, hey, once a request has come in, pods need to exist. It will go and talk to all of the different nodes and it will figure out where to move them. We can, when you tell it different pods, this is how it will end up moving them to actual nodes, and it makes sure that they exist. The kube scheduler has a bunch of different configuration options. When you're creating a pod, you can specify affinity and anti-affinity. You can specify node selectors. If you're like running workloads that need GPUs or need specific behaviors that are needed on available only on certain hardwares, that's when you use node selectors. Taints and tolerations are another fancy way of configuring where your application can live in the Kubernetes clusters, and you have reservations and limits which ensure that the appropriate capacity is available for your service and application. You could also write your own custom scheduler, and there are some people who do that, but I hope you don't have to do that anytime soon. It's actually a fun thing to do, but it's a topic for another day. Next up is the controller manager. As you've seen the name, it says manager. So it's not the thing that actually does a lot of work, but it talks to the Kube API server. The API server owns all of these different objects, things like the namespaces, deployments, services, ingress, and all of these other different objects. It watches all of these with different controllers. You can have like a namespace controller, a deployment controller, a replica set controller. You don't have a one-to-one mapping, but there are a bunch of different controllers. The controller manager ensures that all of these controllers exist, and whenever there are events that happen on the API server, they're passed on to the appropriate controller. This is also where operators fit in. Operators are a very nice and useful paradigm for making sure that all of the custom resource definitions we pass into Kubernetes are actually acted upon, and various resources are created for the requests that we have sent in. And this is one of those cases that you can plug in really well. Let's take a look at how the controller manager actually works. You have a controller manager, there's a namespace that has been created, and there's a node that exists. We go ahead and ask it to spin up a bunch of pods. But before all of those pods exist, a service account needs to exist for the identity of the application that needs to be run, and also there's a bunch of secrets that are associated with the applications running in the container, and it will create these first through the actual controllers for all of these objects, and then it will go ahead and create the deployment, the replica set, and the pod, and those will go ahead and function, and they can only happen when the service account and the secret exist. Similarly, here's another example of the controller manager making sure that a service, endpoint, and a bunch of pods exist, and all of the traffic routing exists the way it needs to be. So that's the controller manager. All of the components that we've looked at so far usually run on what are known as the master nodes or the control plane of the Kubernetes fleet. The next two things that we're going to talk about also exist on the control plane, but are also available in the worker fleet. The kubelet watches the API server. It looks for events around pods or any other objects that need to happen that it needs to watch. And then it goes and talks to the actual container runtime that is configured on our node. In our case, it could be Docker, it could be RKT, it could be something entirely different. It's going to go and talk to Docker, and then it's going to go and tell it, hey, go ahead and create the pod that I need. And then Docker is going to go ahead and run all of those different commands to make sure that all of those containers are created in the appropriate namespace, and then they're created. The kubelet also does a bunch of other duties. It makes sure that the pods that we've created actually live. It ensures that it runs health checks against all of those pods depending on what we've defined, and keeps checking whether the service is up and running or it has died. It also checks for liveness probes, as it calls them, whether the service is ready to take traffic. And this is information that it continuously monitors and keeps sending back to the API server. And lastly, we have the kube proxy. The kube proxy will take a look at all of the different service objects that exist in the API server, and it will go ahead and create them. And it knows how to make sure that traffic is routed to the appropriate pods on the right set of nodes where they exist. Maybe a pod dies because of some, oh yeah, the kube proxy can also be replaced by a bunch of different systems, things like load balancers, service meshes, and all of these are pluggable or replacements that can be used for kube proxy. And it ensures that whenever like a pod dies, traffic is no longer routed to that node and it does not end up being a black hole. And then a new pod comes up and it ensures that traffic is routed to the appropriate one. So this is how a kube actually works. And next up, we're going to take a look at how the network actually functions to satisfy all of the traffic that we just saw, all of the routing and all of the behaviors that we just saw. We've seen so far how all of the different objects in Kubernetes can be created and how Kubernetes ensures that they exist in the appropriate machines that need to live. But what's the point of having multiple services running in different nodes if they can't talk to each other? Let's take a look at how the network actually works and what the administrator needs to know for the Kubernetes cluster. We'll start with a very simple example. You have an ingress that points to a service that points to two pods in a deployment. Before we get to all of these details, we need to understand a few basics. Let's take a look at a pod. A pod is given an IP address. The IP address of the pod is different from the IP address of the node. Whenever you use Kubernetes, each node will usually have an IP address range that is associated with it, and pods are given IP addresses in that range. Similarly, you can have another pod that is created and it will exist in another node. As you can see, it has a different IP. The node of that has, the second node has a different IP, and the range that it has associated with it is completely different. It's entirely up to the network provider how to configure the CIDR ranges and how to ensure that IPs are available. But that's up, and then it's also their responsibility to route traffic correctly through all of these different systems. But how does cluster networking actually work? There are only three simple rules for anything to be qualified as a cluster networking provider. Oh, sorry about that. Let's continue through cluster networking. The first rule that we need to think about is all containers can communicate with each other containers without NAT, without network address translation. Similarly, all of the nodes can connect to all of the containers and vice versa without NAT. And lastly, the IP address that a container sees itself as should be the same IP address that everyone else in the world sees it at. And how does this actually look like? Let's go through all of these step by step. You have four pods. These could exist in completely different nodes, but they should be able to talk to each other. Similarly, you can have pods that are running in different places, and you have these two nodes. Services running on these two nodes should be able to reach these pods on the IP address that is assigned to each pod. And even in the other scenario where pods are running on the same node, it should still use the same IP address to talk to the pod. So this is basically what satisfies the second rule. And lastly, the IP address that it sees itself as is the same that any other box sees it as. So let's go back to our example and try to actually work through all of the different components that make this work. When you have a service can actually have multiple ports. As you can see, our application service has port 2015, which is exposed to the world as port 80. Similarly, you can have the metrics server, for example, running on 2016, which is exposed as port 8080. You can expose the same port twice. So we've done 8888, still exposes port 2015 over here. So there's nothing stopping us from doing that. There are three different kinds of services that exist in the Kubernetes world. There's the load balancer type, the node port type, and the cluster IPs type. All of these have exist to route traffic to various pods, and we'll start with cluster IP as it's the most easiest to understand, and it helps us build up the logic to get to the other types. So you have a service that is of a type cluster IP. We are taking our example. where we have a web app or a web tier that is running in our kubedecon pods, and it needs to go and talk to a bunch of pods that are running caches. Maybe it's Redis, maybe it's memcached. There is a service which we've created for the cache, and it's configured at a cluster IP. It's set to the IP address 10.0.178.1. You could also refer to it as just the name service, cache.kubedecon, so service.namespace of the namespace that you're using, and service.namespace.cluster.local. All of these different DNS addresses or DNS names will always resolve to the same IP address that we have over here, which is 10.0.178.1. And the pods are configured to talk to the IP address of the cache service. What does this actually mean on the node level? Let's take a look. We have pod 1 running on a node, and when it tries to reach to traffic, send traffic to 10.0.178.1, we are going to actually have IP table rules that are going to intercept the traffic that is coming out of this pod for a particular IP address. And then it ensures that this traffic is correctly routed to either of the two pods that exist for the cache service. And we have services and endpoints that exist in API servers, and kubeproxy that is running on each of these nodes actually monitors the service and endpoint objects and updates IP tables whenever things change. So let's say one of our, so that's how traffic is routed to all of these different services. Let's take a look at the next example or the next type of service objects. You have a node port. Let's have two web application boxes that are running over here are pods. They're available on these two different IP addresses, and something from the internet is trying to reach them. We previously set a port on the service type, which you would have noticed over here. I've highlighted, we don't just explicitly specify port 80 and port 2015, but we've also specified 30225. So on the node, port 30225 is allocated, and IP tables catches any traffic that is coming to these ports, and then it ends up routing that traffic to the appropriate pods. So we have a mobile user who's trying to reach our service. They end up at port 30225 on our second node, and IP tables is then going to route traffic either on a round robin basis or other logic to the pod on the same box, or it could also go to traffic or send the traffic to the pod on the other box. Similarly, you have another user. This one ends up getting connected to the other node, and IP tables is going to do the same thing. As some of you would have recognized by now, this is not really a very scalable solution, and it gets us to a point where users will keep switching between different pods, and they will not have a great experience. For our sample static site, nobody cares, but for an actual application, this is not a great example. And this is where the load balancer type comes into picture. The load balancer still uses a port on the node. It still uses the application ports, just like we did for the cluster IP and the node port. But here, when traffic is trying to reach all of these boxes, we have a controller manager, and controller manager watches all of the services that are defined, and then the controller manager reaches out to the cloud provider. In our case, it would be someone like AWS. It will go and run the appropriate API calls, which is going to then go ahead and provision a load balancer. All of our clients are going to go talk to this load balancer, and then the load balancer will send traffic to the appropriate node port. And finally, after all of this, traffic reaches our pods. There are a few other interesting projects that are super relevant in the networking space. I absolutely love external DNS as an idea. It lets you expose all of the different services that exist inside a Kubernetes cluster as DNS records, and it is provider agnostic. So you can hook it up with Route 53, with Google Cloud DNS, Azure Cloud Map, Cloudflare, and so many other different resources. Another thing that is the bread and butter for Kubernetes clusters on AWS is the VPC Cni. This ensures that all of the fancy and insanely awesome features that the VPC provides us for elastic network interfaces is available to all of the resources that are running in Kubernetes. You have a plugin that is set up on Kubernetes, and then you have a daemon that runs on every node to manage all of the ENIs. And lastly, we have various controllers that can create load balancers for services. If you're talking about a service, it'll end up creating an NLB, And if you're thinking of an ingress, it's going to think of and create an ALB for us, and it's going to create them for EKS clusters. So this covers our journey for how the network works. And we're finally at the last leg of this presentation. Let's take a look at what are some of the interesting cloud projects, especially by AWS, that make it much more easier to run Kubernetes. I'm going to be Captain Obvious and first talk about Elastic Kubernetes Service. We have seen people who run their own Kubernetes clusters, and they all hopefully have very good reasons to do that. But as someone who is a fan of AWS and managed services, I would highly recommend Elastic Kubernetes Service. They ensure that all of the control plane that is required to run Kubernetes is healthy and performant. They will set up all of the ACD clusters, the control plane nodes, and even make sure that all of the Kubernetes packages are up to date, and they keep you as close to the newly released external GA versions as possible. You can either pair it with Fargate to run a bunch of your workloads, or you can spin up your own fleet of EC2 managed worker nodes that you can then hook up with this Kubernetes cluster and run your workloads on. We also just talked about the load balancer controller. This ensures that the appropriate AWS resources are created so that traffic that reaches the AWS edge regions or the AWS network edge reaches all of the various pods and containers that we use for running our applications. Next up is a super interesting project that I'm really looking forward to see grow a lot more. This is the AWS controllers for Kubernetes. Today, it creates things like SQS queues, SNS notifications by taking in custom resource definitions and then spins up all of the actual underlying cloud resources. This gives you a uniform interface to all of the cloud resources that you need to work with, and then you don't need to take a look at things like Terraform or even CloudFormation and step outside of your Kubernetes YAML world to run your entire project. Another project that I dearly love is the cluster autoscaler. This is a Kubernetes project that makes sure that you use your systems very effectively, whether it comes to scaling up when you get more demand or scaling down to save costs. And my systems and my team systems could never have functioned effectively and efficiently without cluster autoscaler. And last but not the least is Iam Authenticator. We all have a love-hate relationship with AWS identity and access management, but we know that it is absolutely essential for us to run any services on AWS. The IAM Authenticator is where IAM meets Kubernetes role-based access control model, and it gives you the best of both worlds to ensure that only the right set of people can create resources in your project, and also ensure that the wrong people can't access anything that they shouldn't be accessing. And with that, we come to the end of our presentation. I would like to thank Carson Anderson for creating the original Kubernetes Deconstructed session that I absolutely loved and learned a lot from. He presented this at KubeCon a few years ago, and I took the liberty of modifying this for AWS. I've also taken a bunch of artwork for all of the different icons that we've used, whether it's from the official logos on CNCF, Docker or AWS architecture icons. And I would also like to thank openclipart.org for all of the clipart work that you've seen. Thank you so much for attending this session. I hope this has been really helpful for you, and this gives you a better set of tools and a better mental model to work with Kubernetes in the future, not just be a simple user, but be an enlightened user and hopefully on your path to mastery. Are there any questions that I could help with?
All right,
Hey.
Ninaz, that was a wonderful teardown. Thank you for that. Quickly, if there are any questions, please do post it in the chat. In the meantime, we have actually opened up the quiz for this session. So you should be able to see it on your screen right now. So the quiz is quiz-t1s2.awsug.asia. You should see a QR code on the screen as well for participating in the quiz. So we'll keep the quiz open for 5 minutes. In case if anyone does have any questions, please do post them in the chat.
And while we wait for the questions, I would just like to briefly apologize for some of the video delays. We had a couple of technical glitches on the entire organizing side. We'll do our best to make sure that when we upload this to the recordings are uploaded to YouTube later, they'll be in a better condition that everyone can follow along. So just sorry for that. Does everyone already understand Kubernetes? Looks like everyone's an expert already. Then my job's done here.
So I think there is one question, Ninant. Can we use the same node port in different pods running in different nodes?
Can we use the same node port in different pods running on different nodes? Yes, of course, because the node port is going to be only used for an individual node. And you can, with the typical Linux behavior, the same port on the same box cannot be used by multiple services. But if they're running on different nodes, then of course the port you're using is going to be available on the other node, and then nothing stops us from running them. And even in certain cases, if you look at things like Apache, you have the same port that can proxy, or HA proxy or other systems. They can take an existing port and proxy it to multiple backend services. So even if you're running the same pod on the same node or multiple copies of it, Kubernetes will ensure that the traffic reaches it in a round robin manner. So I hope that helps answer the question.
I think we have one more question.
Yep.
That is, sorry.
No worries.
How do we resource usage of
Control. Yep. So a Kubernetes by default affords us two controls that we can set up on the usage of various resources on the system. You can control how much memory is allocated to a pod, or rather, how much memory should a pod take at the most, and the same way, how much compute capacity can a particular pod take. You can specify that in the resource section in your YAML, and there's also a limits section. The way this works is, if when you set up a resource configuration, Kubernetes ensures that when a pod spins up on a particular node, that node actually has the additional like 400 or 500 memory, that MB of memory that is required for the pod to run. And if the node only has like 200 MB of memory remaining, it will not schedule the pod on that box. It will schedule it on a different box. And by limits, what happens is, the moment your pod crosses the 500 MB of memory, in a typical Linux scenario, the OOM killer will kick in, and it will also terminate the pod for excessive usage of memory. So this is how you end up controlling your pod's resource usages. So far, I've mostly used resources and limits for CPU and memory, and over time there might be other approaches or other resources that you can control. Any
All
other
right, we have the
questions that
quiz
we could
open
help with?
for, yeah, we have the
Sorry,
quiz
go
open
ahead.
for 1 more minute, Ninat. And I think there's one more question. If you could quickly answer that, just as we are closing the quiz.
Sure. This is actually not a great question for me, because I've personally not worked a lot on the security side of the Kubernetes world, but I'll do my best to answer this. Along with the API servers configurations on who can authenticate with it or not, especially if you're in an AWS world, you want to look at the Iam Authenticator that I briefly touched upon at the end of the session, and ensure that the right set of people or the right set of AWS roles can go and make various changes in Kubernetes, whether it is creating new pods, deleting old pods. That's something that you want to probably limit. So you make use of everything AWS IAM and Kubernetes RBAC, and you add a lot of security. There's a lot more that can be done in security, and I would probably look up some of the CIS benchmarks on Docker and Kubernetes security to ensure that your systems are safer. I'm not a security person, so don't take my word for like the That's the final word. Cool. So I think we're at the end of questions. I would like to just end off with a small note. My team is hiring for a bunch of different reliability engineering positions, and I think Satya or someone from the group will be sharing the link for that later. I'd love to talk to you if you're interested in running systems at a large scale, and we should probably chat outside this session. Anything else we want to do, Faisal, before we close this off?
I don't think the quiz just closed out, and looks like we have 3 toppers there. One is Pranavi, who's got 3 correct answers, and then there is Yasas and Nasiullah. So top 3 on this quiz. So keep attending the other quizzes, guys, for the sessions. And Ninad, once again, I want to thank you for giving that wonderful breakdown for the session.
Thank you.
Build. Go. Build. Go. Build. There is no compression algorithm for experience. Def and test are the most important workloads. Dance like nobody's watching. 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 Encrypt like everyone is.